Okay, the purpose just to show we choose this example not just because it is simple, because it can be used to model many real world systems. Now, of course, we are going to use the state space model. Okay, so we need to convert this one into a state space model. You first, your first homework assignment, you have a similar problem, right? You have a system described by a differential equation. You want to put it into a state space model, okay, under zero order whole. Anyway, you first get the state space model for the continuous time, right? And then you get ABC. From that one, you will have this formula to get your phi gamma. So here I will ignore those details. I just directly write down the discrete second order system, the state space model. Okay. And then we want to design, right? We want to design the controller to place the pose, to change the pose. First of all, right? Without feedback, what are the pose? What are the pose for the system? One, but it's a repeated one. So therefore, is the system stable? It is unstable. It is not even marginally stable because the one is a repeated pole. We emphasize that. So it is not stable. Then we need to build a feedback controller to change the behavior because the system is unstable, right? Then we need to place the poles, right, to some desired positions. Can we do it? Then we say, okay, let's try the proportional control or the state feedback. Okay, so minus Rxk. If I write down the individual terms for the air is just R1, R2, right? Just an inner combination of the state variable. And then we want to find out what is the R1 and R2 to meet the requirements. Okay, then let's just plug this expression into the system, right? So this is the model. Now, and then we replace this u by minus L x. The overall we get phi, right? This one is gamma times L x, right? Phi minus gamma L x. Now you already notice for the original open loop, right? The matrix is phi. So after feedback, now the matrix changed into phi minus gamma L. So the system matrix has been changed by feedback. That's the whole point of feedback. It will change the property of the system, right? Because the eigenvalues of this matrix, phi, has been changed, right, to the eigenvalues of this different matrix, phi minus gamma L. And the L are the design parameter. We can change the pose. Okay, this is where we are. We want to compute what is R1 and R2. Now this is one way. Just plug in your equation into the closed loop. You want to find out, right? You want to find out the pose of this closed loop, which will depend upon your R1 and R2. So how do we design the control gain L? So let's do the calculation. So this is gamma, this is L, right? We do the matrix multiplication, right? We get, okay, this one will be a 2 by 2 matrix. Then there's phi minus gamma L, right? We already know phi, right? Phi is here, minus this gamma L, we get a different matrix from this original, right? 1, 1H. Then we can compute the correlative polynomial of the closed loop of this phi minus gamma L, which is this is the way you compute, right? The I is identity matrix. So therefore, this matrix, it will change, right? The diagonal term, the I, so the Z minus this one, so Z minus this term, then those two terms, there's a minus sign, right? Change the sign. That will be the meaning of this matrix. And then you try to compute the determinant of this matrix. The determinant of this matrix, that will be the characteristic polynomial of this matrix phi minus gamma L. Okay? Of course, then you know how to compute the determinant, right? This term times this one minus, okay, the multiplication of those two. After some organization, you end up with a second order polynomial. From this polynomial, you can tell there are two coefficients here in this polynomial, right? Those two coefficients depends upon the gains L1 and L2. Okay, this is where we are. So we use the feedback control, right, or the proportional control. Then we change, right? We change the characteristic polynomial of the system. Now the coefficients depends upon the gains. Then you see how we're going to place the poles to the desired position. Okay, we just compare this polynomial with the desired characteristic polynomial, which you already know from the reference model, right? Okay, here for the pole placement, right? Okay, for the pole placement, because I want to match the poles, the easy way, right? Just directly match the polynomial. You match those two coefficients directly. You don't do it in a very direct way. You say, okay, I compute the two poles, or I also compute the poles of this quadratic equation, right? You put those two poles the same. That's another very direct way, but that's not the easy way. The easy way, you try to match the polynomial directly. If you match the polynomial, of course, you match all the roots. Okay? How are we going to match the polynomial? Of course, you just match the coefficients, right? Then you match the coefficients, then you say, okay, this guy has to match P1 and this term has to match P2. Look at those two equations. There are two equations, and then there are two design parameters, L1 and L2, right? So we can easily solve the problem. Yes, we can easily solve it. I can compute L1 and L2. And then, of course, L1 and L2 depends upon P1, P2. The problem has been solved. Now, so this is the one direct way to solve the pole placement problem, right? You plug in the expression of the controller into the model. You try to compute the characteristic polynomial, and then that characteristic polynomial, your coefficients of that characteristic polynomial right here will depend upon your design parameter. You try to match those coefficients of this desired polynomial, right, of the closed loop system to the desired one. Match the coefficients. Then you will have a set of equations. You try to find out whether you can solve the equations. Okay, then you get the answer. This is one very direct way for doing this. Any questions? Well, for this double integrator, now we can answer the question: is it possible to design the controller to place the poles to any desired location? Yes or no? Yes, because right, for any desired location, right, which means I can put any value of P1, P2, but that doesn't matter, right? I will, as if I know P1, P2, I can compute my L1 and L2 to make the match. Okay, now the poles can be placed anywhere you like, of course, not because of the power of feedback. But can we do this for any other linear system? Right here, we only solve the problem for a very special case. Of course, we want to know, right? How about a general case? Okay, let's find out the answer. To answer that, right, this is the time we want to use the controllable analytical form. Okay, we first say if a system is in the form of a controllable form, last time I mentioned, right, that it will make the design very simple. Now let's try to see how it can help us to solve the power placement problem. So we say this is the controllable canonic form. Okay. This phi, right, phi theta has the first row is the long trivial row, right? All those coefficients are taken from the transfer function, from the denominator of the transfer function, and all the other rows are completely fixed in this form. And the gamma theta is also in a very special format. Only the first element is 1, all the other values are 0. Like I said, this those for the first row, the elements in this first row are taken from the transfer function, from the denominator of the transfer function. Okay. Now, let's try to solve the problem, right, when the system is in this form. But first, right, I give you this information now. Can you answer this question? If you know this is the canonic form, right, you know the controllable canonic form, how do you get the characteristic polynomial for this matrix? You just use this, the first row. Is that clear? Right? You take the first row. The first row will decide the characteristic polynomial because I already tell you how you get the controllable canonic form. There is a correspondence, right? The first row, those numbers correspond to the numbers in your denominator of the transfer function. And you know the denominator of the transfer function is the characteristic polynomial of the system matrix. Right? Okay. This is important to remember. The correct polynomial, right, can be taken from the first row for the controllable canonic form. Now, let's look at the state feedback controller. Okay, I'm going to design a controller, right, state feedback, so air. Then we want to say what happens to the closed loop if I use this controller. Okay, and then I plug it in. So the U now is minus LZ, right? So here I get this phi minus gamma L times Z. Now let's look at the what is the gamma L? Gamma times L. This is the gamma, right? 1, 0, 0. If I multiply by a vector, a row vector, easily you know that this will be the form of this matrix, right? Only the first row, right? The first row are non-zero numbers. The one, right, multiplied by all those numbers. All the other values, right? All the values are 0. Is that clear? Okay. So this is gamma times L. And then we can now, because this is gamma times L, so we can easily compute the phi minus gamma L will be in this form. Okay, so this is where we are. If a system is in the controllable canonic form, right? If we use our state feedback, this is the system matrix after the feedback. You look at that. Let's take a close look at this matrix here, phi minus gamma L. Let's look at the first row, the long trivial row, the long trivial row. Does the feedback controller change the long trivial row? Actually, it can change, right? Every element, right, has been changed by the gains. Every element of the long trivial can be changed independently, right? The L1 can change the A1, L2 change A2, Ln change AN. Then how about the trivial rows? Those trivial rows. Does feedback affect the trivial rows? The trivial rows is not affected. Why? Because the error, right? Oh, the gamma takes a very special form. Gamma, only the first row is 1, the other values are 0. A very special form. That's why it only affects the first row, does not affect the other rows. So the trivial rows keep the same. The input does not change other state variables directly, right? Which will simplify the controller design. Now, if you look at this matrix, phi minus gamma L, you look at this form, is it still in the controllable canonic form? Yes, right? You only have one non-trivial row. The other rows are completely fixed. They are the same as any controllable canonic form, right? So therefore, it is still in the controllable canonical form. Well, now you should tell me, there is a simple way to get the correct polynomial from the controllable canonic form, right? Do you remember? How do you get the controllable canonic correct polynomial from the controllable canonic form? You just look at the first row, right? You look at the first row, and then you can immediately write down the correct polynomial, right? Which is just, right? Those are the coefficients of the correct polynomial. That will be the closed loop correct polynomial. And now the answer should be clear now. If we compare this with the desired correct polynomial, can you design your L1 and L2, Ln to match those coefficients? And the answer is very simple, right? I want to match this P1, of course, A1 plus L1 equals P1. So L1 is just P1 minus A1. You see? Trivial, so you get answer, very simple answer. When a system is in the controllable canonic form, you just design the gains such a way that just take the difference of the coefficients, right? For each coefficient, take the difference. P1, this is the desired coefficient. This is the real coefficient. Take the coefficient. That will be the gain of the feedback control if a system is in the controllable canonic form. Okay, how easy it is if it is in the controllable canonic form. Okay. So here is the final answer. If a system is in controllable canonic form, right? I mean, this will be the design. This will be the controller. Use a very beautiful solution. But of course, we have to answer the question, right? How about the system in other forms? Then we have to relate any other system into the controllable canonic form. Right? Can we transform any linear system into controllable canonic form? What is the condition? Of course, right? What? It should be controllable. If a system is controllable, there exists a transformation, right? Transformation of the state variable, transformation matrix T. It can transform it into a controllable canonical form. If the Hubbard system is uncontrollable, if a system is uncontrollable, can you transform it into a controllable canonical form? Cannot. Remember, if a system is in a controllable canonical form, of course it is controllable, right? So if a system is uncontrollable, how can you make it into controllable by a simple mathematical trick, right? It cannot happen in reality. So therefore, we know that it cannot happen. It has to be controllable, but if it is controllable, we can do this. We can do this. Okay, then how are we going to design the state feedback for the general form? Okay, if a system is controllable, then the design is very simple because we know the answer for the controllable canonic form, right? We design the controller for the controllable canonic form first. So we know the answer, right? We know the answer, and then this is supposed to be the controller. But of course, we cannot use the z directly because the state variables, right, are x instead of the transformed one. But we know they are related, right? They are related. So x can be computed from z. Therefore, you just replace the z by t times x. That will be the answer. That will be the answer. Of course, in this design, you say, how about t? I have to know the t. Yes, you can compute t. And it can be shown by Cayley-Hamilton theorem again, but we're not going to show that, right? It's a bit involved. This final answer for this error, right? Because here this is the error tutor, and then it has to multiply by t. If we put them together, this will be the formula. It can be shown that actually this is the way you're going to compute your error. Here, this error right here is a raw vector, a very special form, or element 0, only the last one is 1. Here, it involves the inverse of a controllability matrix. So therefore, it has to be controllable. If you want to apply the Ackermann's formula, then how about those AM5? The AM, that is the characteristic polynomial of the reference model, AMZ. So when you evaluate that, right, you just put those Z with the matrix 5. Okay, that's the how. Okay, now here, let's look at the example. Okay, we will look at the design example, but the whole problem becomes an algebraic problem. You are given a pair, phi and gamma, right? This is from the system model, state space model. You try to find the error such that phi minus gamma L has any desired eigenvalues. You want to change the eigenvalues? We know that eigenvalues are the poles. So, okay, we can say we have an answer. We can choose the error such that the correct polynomial of phi minus gamma is any desired one. Let's look how we're going to use this formula. Okay, let's look at the double integrate example again. We solved this problem before, right? When we try to solve that, we use a direct approach. We get the correct polynomial, but we didn't use the Ackermann's formula here. Let's see how we're going to use Ackermann's formula. You have to compute the WC, right? The controllability matrix, which is the first row is gamma, this vector, this second column, that is phi times gamma, phi times gamma. Of course, it is controllable, but you can easily verify. This matrix is non-singular. Then we apply Ackermann's formula, right? We have this WC, okay, and then you can get the inverse of this matrix. This how we evaluate this AM phi. Like I said, right, the AMZ is the square plus P1Z plus P2, right? You replace Z by this matrix phi. That's the meaning of this term. It is still, right, it is still a 2x2 matrix. If you multiply them together, right, you do the calculation, I mean, this will be a 2x2 matrix. Okay, and then the final answer, right? You multiply those three by this row vector times this matrix, you will get this answer. This is, of course, is the same answer as what we did before. Compared to the first method, this is the way we have done, right? We solved the problem at the beginning. We have this matrix phi, right? And then we know the gamma. We try to get the determinant of this, or determinant of this matrix. That is the correct polynomial of the closed loop, right? We say, okay, that polynomial will depend upon the L1, L2. We let this polynomial match the desired polynomial, you get a set of equations, right? And then you solve for L1 and L2. That is the first method. Here, you can show there is another method. You use the Eichmann's formula. Okay, there are two ways to solve it. Which one do you prefer? The direct way or the Eichmann's formula? Which one? Probably, I guess I want to have a sense about your performance. Okay. You can please raise your hand if you prefer the Eichmann's formula. Nobody want to use Eichmann's formula? Everybody want prefer the first one? Oh, okay. Okay, which in some sense actually, because Eichmann's formula is like a magic formula, right? You plug in and you don't know why it happens. Okay. The first one is very direct, right? Step by step, you get the answer. Okay, let's look at the special case. This is what we call the deadbeat control. The question for deadbeat is that, okay, can we drive the state to zero in n steps? Remember, right? We want to make the state go to zero. Can we do it in finite time? Actually, in just n steps. Well, let's say there is this is a special property for the discrete time. It can happen. Okay, now we have the system equation. We use the state feedback. Then we have a closed loop system, right? It will change the matrix from phi to phi minus gamma L. Then the correct polynomial of the closed loop matrix phi minus gamma L is here. Okay, we match the desired one. Let's say I already designed my L, right, to make this. Now, let's put the desired polynomial or the closed loop polynomial in very special form. I want to place the poles to zero. If all the poles are zero, what are those coefficients? P1, Pn, what are those coefficients? I want to make the roots to be all zero. What are those P1, P2, Pn? Zero, right? Then all the poles will be at zero. Okay? Very special case. The order, so there are multiple poles, but is the system stable? Is the system stable? Come on, classic. You shoot your head. Zero. There are multiple zero for the discrete time. That is the most stable position, right? So even though it is I mean, it is a multiple, of course, it is very stable. It is very stable. Now, but here is the answer I want you to tell me. I know this is the correct polynomial of this matrix, phi minus gamma L. And I know, but now I put this closed loop. This is the correct polynomial in a very special form. It's just there to the power of n. Now, I'm going to replace my Z with the matrix phi minus gamma L. What is this value? Very good. From the Cayley-Hamilton theory, the matrix satisfies its characteristic equation. Excellent. Cayley-Hamilton theory tells you this must be 0. And now we can use this property to show the deadbeat. If the controller is implemented at time k, and we apply this one, right, n steps, so xk plus 1, right, then the next step is just phi minus gamma L xk. xk plus 2, right, is just phi minus gamma L square xk. At the n step, xk plus n is phi minus gamma L to the power of n xk. But what is this? Phi minus gamma L to the power of n? 0. So we can drive the state to 0 in finite time. Can you do that for continuous time system? For continuous time, no matter where you place the poles, right? All the numbers, right? Because you cannot place the poles to minus infinity. The only goes to 0 exponentially, right? It will not go to 0 in finite time. Okay, is that clear? So deadbeat is a special property for the discrete time. But say it's so good, but there is no free lunch. So deadbeat is rarely used in practice because to make that the energy consumption is too high. Or in other words, right, the magnitude of the control signal have to be very big to achieve that. Okay, any questions? So here again, you can say the power of the Cayley-Hamilton theory. Well, finally, we have answered the question, right? What if the system is uncontrollable? What does that imply? We know that if a system is controllable, we solve the problem. We have Ackermann's formula. Let's just check out this example. The system is not controllable. This can be easily seen, right? By if we look at the controllability matrix. This is gamma, right? This 5 times gamma is A0. You can say that this matrix is singular or non-singular. Singular because, okay, those two rows, right, those two columns are linearly dependent. Now, actually, there is another way to say without looking at the, another way to say this is by drawing the graph. So you say, okay, x1 and x2. Then you look at the equation, okay, the first equation says that the x1 depends upon x1 and x2. So x1 depends upon x2. And also as affected by input. Right? Then how about x2? The x2 actually depends upon x2. So from this graph, you can easily say, does the input affect x2? No connection, right? So that's another way to say, okay, it is not controllable. So in other words, right, the x2 is running by itself. But x2 can't affect x1. Okay, fine. But of course, algebraically, right, just to get the controllability matrix, you know it. And then we say, now, if this is the case, can we use Ackermann's formula? Ackermann's formula involves the inverse of this matrix, right? So now you say, okay, I cannot do it. But can we still use the state feedback control? So why not, right? Why not? Of course, we still use it. Even though you don't know the Ackermann's formula, it's good that everybody prefers the first one, right? We can do that direct way. So let's say we do it directly and then find out where can we design the gains, right? Can we design L1 and L2, right? Place the pose. Let's just do it, right? So we compute, we plug in this one into this equation, and then this will be the matrix after the feedback. Now you look at this matrix. Look at this matrix. Without even go further to compute the correct polynomial because of this special form. What are the eigenvalues or what are the poles of the closed loop? Right, A minus L1 and B, because it's in a triangular form. Is easier. So those are the poles after the feedback. Now you will notice something. If I look at the original system, what are the poles for the original system? Is A and B, right? So now after the feedback, you can design the both L1 and L2. Can you design L such that the poles can be placed to any desired position? You already know I can only change one of the poles. The other poles cannot be changed. Right? Clear? So the pole, the A can be changed, but this B cannot be changed. Okay. But that once a system is uncontrollable, right, does not mean it's hopeless. It depends upon the poles which you cannot change. Maybe those poles are stable, right? So if the poles still less than 1, right, this controllable mode is stable, then we call such kind of system stabilizable, even though it is uncontrollable, but it is still stabilizable. If this one is bigger than 1, since this mode is unstable, then there's nothing we can do to control this system, unless we make major changes to the system. Okay, let's summarize what we have learned. So we use the proportional control, very simple way. Very simple controller, right? The input is just the linear combination of the state variables. Then we have a closed loop system, right? Now the matrix change from phi to phi minus gamma L. If a system is controllable, the poles can be placed anywhere. Those desired poles are specified by the reference model. If the system is uncontrollable, then some of the poles cannot be moved. If the uncontrollable poles are stable, then one can still control the system to some degree. If the uncontrollable poles are unstable, then we have to make major changes to the original system such that the system becomes controllable. Now, finally, can you suggest a simple way to change the controllability? So you look at phi and gamma. So which one is easier to change? Gamma. But when you change gamma, what does that imply? It means that you change a different type of input, right? It's like, you are having you are sick, you take one medicine, it doesn't work, you change another medicine, another type of input. Or in other things, like if you, let's say if you are driving a car, now you try to control the direction or the movement of the car. So the position of your car, right? The direction of your car is the output. Now there are two inputs. One input is your steering wheel, The other input is the accelerator. If you use the accelerator, is the system controllable? Which means you use the accelerator to control the direction of your car. Is it controllable? Not controllable. So you have to use the correct input. You use the steering wheel. That is the correct input. Now it becomes controllable because you have to use a more effective input, right, to make it controllable. All right. But mathematically, when you do that, it means you change gamma. Okay. All right. But there is one serious limitation of this controller, right? Is the way this form. It means that I need the measure all the state variables, right? I need the information about all the state variables. How do we overcome this limitation? That will be the topic for the next time. So let's have a 50 minutes break, then we will continue.
Hey guys, welcome back to Control System Laboratories. I'm working on my big flashy entrance here, so hopefully I can grab your guys' attention right off the bat. And, well, now that I have you, in this video I want to show you guys a really simple feedback control system for a robotic car, like this one. And in doing so, I want to show you sort of the differences between commanding open loop versus commanding closed loop, and how closed loop control can help you meet your design goals for your system even in an environment that's changing due to disturbances or just uncertainties in the environment itself. Now, before we get started, let me really quickly show you the components that make up this robotic car. So this is the robotic car that I'm going to use as my test platform. It's mostly just a stock Zumo robot from Pololu.com. I got the kit rather than the fully assembled vehicle because I wanted to practice my soldering. But if you're not into that, you can always just get the fully assembled car. Now with the kit, you get to pick your own micro metal gear motors, and I chose 2 of the 50-to-1 gear ratio high-powered motors for my project. These 2 motors are the ones that drive the front wheel for each of the left and right side. Now, the Zumo Shield, which is this big black printed circuit board, can be modified to interface with various versions of the Arduino microcontroller. I set mine up to work with the Uno, because that's one I have, and the instructions tell you how to do this, but basically it's just soldering these header pins in the right pattern so that it matches the Arduino. Now the Zumo Shield has a few sensors on it that you have access to. However, I wanted to use an external sensor because I think it makes more sense for this educational video if you can actually see the sensor that I'm using. And that's why I have these wires protruding from the front here. They allow me to connect to this I2C external bus component. Now I2C stands for Integrated Circuit, and it's a way to send information between 2 different ICs, much like a telephone wire between a sensor and a microcontroller. Now if you don't know what any of this means or how to write code to read an I2C device, don't worry about it. There's a few libraries online for the Arduino that do all that work for you, and I'll get to that in a second. Now as far as my Arduino, this is unmodified. It's just an Arduino Uno, and I happen to stick this breadboard on the back using the adhesive that comes with it so that I have a place to attach my external sensor. And if I put this all back together, you can see what the final product looks like. And again, I can plug in my I2C bus into the breadboard, and then I can plug my I2C component into the breadboard also so that everything can now read each other. Although for this first example, I want to control the car open loop. So I'm going to remove the sensor for now, and let's go set up the test. Now I want to have the car drive from this side of the platform over to this side and make it to this flag. Now it's just a straight line, and I've drawn the straight line in black here on the platform so you can see it a little bit easier. But the trick is I want to command this open loop, which means I need to be able to predict how to send commands to the car in order to accomplish this. Now, luckily it's just a straight line, so that makes it pretty easy. All I have to do is send the exact same command to both wheels, And if I built the car correctly, they'll both spin at the exact same rate, and the car will just drive in a straight line across the platform. So let's go write the code for that and test it out. Now, if you're not too familiar with writing embedded code, don't worry, neither am I. But luckily you can download the Zumo libraries for the Arduino directly from the Pololu website. You can either just do a search for the Zumo Robot Kit, or you can click through the links to get to it. But once you're there, click on the Resources tab to find out all of the different files that you can download. And under the Zumo Shield Libraries link, you're going to find the files that we're looking for. And there's libraries here to drive the buzzer, the motors, the sensors. You can download all of them if you want, but we're only going to be using the Zumo Motors library for this example. To download them all, just click the zip button up at the very top. And once you download them, put all of the files into the library folder for the Arduino.
All right, welcome back. So this is where we are. So we've shown that with a very simple state feedback, we can place the poles to anywhere we like if the system is controllable. But the problem with this controller is that, right, we need the state variable. We need the information about all the state variables. In many practical problems, we may have only one sensor to measure the outputs to save the cost. So the output is available, not all the state variables. So how do we solve the control problem? Okay, if we face such kind of issue, right, in the real world, we can either build a new control system or we just modify the existing technology. And normally that the second way is more the second way is cheaper, right? It's cheaper, can save cost. So which way is simpler? If we want to just modify the existing one. So we still want to use this one, but we have to solve the issue that actually we only have the output signal, not the state variable. The how we going to get the missing state variable? Then the question becomes, is it possible to estimate the state variables? If yes, then we can just replace the state vector with its estimate, right? Let's say estimate is x height. So that's the whole idea for this approach, where that we only have the output signal. Okay, then how are we going to estimate the state vector with the input and output? Then we need to build observer to estimate the state variables. But here, just be cautious. The term observer is just a algorithm, a program. Okay, it's not a hardware, a sensor. So, all right. So let's think about how we're going to build an observer. Right, we want to build an algorithm which can estimate the state variable. But remember, we already have this model, right? The model is already available. You know the phi, gamma, c completely. The only missing information that you cannot measure the state variables directly. Okay. If you know the initial condition, right, and then of course you can compute that exactly, but we don't know that because if I don't know the state variable, of course I don't even know the initial condition of the state variable, so I cannot use it directly. What is available is just the input, right, and the output. So I know the output y. But you say, hey, a very simple way we think of is that, hey, I have the model, right? Therefore, I just use this model. I compute my state vector, right? Now I don't know the actual value, but I just use this model, I compute my x height. With exactly the same model, I compute that. Will that work? So I have two systems, right? I keep a copy, I know the model, and then I just use it. This is what I call the naive observer, where we say what could be the problem. I know. So I just use the model itself. I use the input signal. I have the model, I try to compute the output and see whether it will be the same. And then I use this model to compute my state vector x height. Hopefully, they'll be the same as this state vector, right? But we have to be careful, right? We have to do some other analysis and say whether the estimation error will go to 0. Let's do a simple calculation, right? So we have the two equations. Let's put the first equation here. This one x k plus 1 minus x height k plus 1. So on the right side, we have those phi. So x minus x height, the gamma UK disappear, right? So this is what we have. Therefore, if we define the estimation error as the x minus x height, then we have the dynamic equation for the errors. You look at this equation, so the error at the next step depends upon the current error multiplied by the matrix phi. So the matrix describing the error dynamics is the same as that of the system. Now, if you look at this one, what is the condition for this error signal to go to 0? What's the condition on phi? Such that this signal, the E will go to 0. The system has to be stable, right? The system or the eigenvalues of this phi have to be, right, stable. So therefore, only if the system is stable. If the system is unstable, your estimation error will blow up, right? It will be very big. Now, so you can say by simply using the original model doesn't work. So we have to try something else. Now let's look at this observer again. Does this, if you look at the equation of this observer, right? Does this observer use the information about the actual output? Look at the equation. Yes or no? Does it use the information about y? No. Right? So therefore, are there any feedbacks to this observer? Feedback means I use the information about the actual one, right? I don't use it. So, okay. So now let's try to improve this observer. Now I have this observer. We know, okay, that this observer will compute the estimated output. What is the desired value for the estimated output? Is the actual output, right? You know the actual output, and this is the computed output. Okay, I want to make this y height go to y. Okay, and then can we use feedback mechanism to improve the observer? Feedback means, right, you measure the actual output, you compare, and then you do the correction. You measure, you already have, right, you compare. I would compare with the actual one, and then I do the correction. Since it's a linear system, so the correction term normally is proportional to this error. Okay, let's try this. A very simple idea, but it's still based upon the feedback, right? I know the desired value. I look at the actual value from this observer, right? And then I want to make this error signal small. Okay, let's try the feedback. So therefore, now let's look at the new form of this observer. In addition, right, to the original model, I add something else. Those are the correction terms. Okay, and with this term, let's try to analyze the dynamics of the error signal. This is the model of the system. This is the observer. We are interested in the difference between x height and x, right? So x minus x height, xk plus 1 minus x height, right? This right side, this 1 minus this, I will give phi, x minus x height, gamma uk disappear, right? But I have this minus k, y minus y height. Okay, is that clear? Now we know we just plug in the expression of y and y height, right? Y is just cx, y height is x height. And then let's define the difference of the state variable as this is the estimation error, right? We get this one is ek plus 1 phi. This is ek here, right? This is cx k, and this is cx height k. That becomes k times cek. So finally we have phi minus k times cek. That is the dynamic equation for the estimation error. Well, you can say the feedback has changed the aerodynamics, right? Without feedback, it is phi. Now it becomes phi. The matrix changed from phi to phi minus k times c. Remember, k is a design parameter, right? You can use k to change this matrix. Okay? Can we design k such that phi minus k is stable, right? Okay. Now let's record the problem, right? Here we design an observer. This observer evolves again on the output arrows, okay? And then the dynamic equation for this arrow signal is phi minus kc, this matrix. Given any pair phi and c, can we choose k such that phi minus k times c has any desired Charlotte polynomial? A lot. I didn't know this A naught is different from the reference model, right? But it's another polynomial I want to match. Of course, the pose of this polynomial will be stable. But remember, right, in the first half, we have already solved a very similar problem. For the power placement with the state feedback, given the pair phi gamma, we find air, the gain of the for the controller such that phi minus gamma L has any desired correlative polynomial an. We have the Eichmann's formula for that. It is possible to apply this formula again, but there is one more obstacle to clear. Those two problems are not exactly the same. Okay, let's compare. We're given phi, this matrix phi, right? We want to design my k such that phi minus k times c. C is also given, so k is a design parameter. I want to make the eigenvalues, right, of this matrix, right, match some desired ones. Now on this problem we have solved, this phi, right, we're given phi and gamma, we are going to design air. And the solution is given. The difference is that the design parameter, right, for this problem appears on the left side. When we try when we derived the Eichmann's formula, right, to solve this problem, those design parameter L appears on the right side. And we know that in matrix, right? I mean, if we cannot change the sequence matters, right? So we cannot directly use this formula. So therefore, we have to apply a trick to make the design parameter appear on the right side, not on the left side. If this design parameter appear on the right side, and then I can use this formula again. Then it becomes a algebraic problem, right? What is operation which I can make this k appear on the right side? You do the transpose. Do the transpose. Okay, so you do the transpose on this matrix. Then you get the phi transpose minus C transpose times K transpose. Of course, the question is, well, how about the eigenvalues of our matrix after the transposition, right? Are the eigenvalues the same for A and its transpose? We know that they are the same. The transpose will not change the eigenvalues. Okay, so therefore, we just solve this problem, right? We're given phi transpose, given C transpose. I'm going to design my K transpose such that, right, it's the pose or the eigenvalues of this matrix are the desired ones. Then now we can apply this formula, right? We can apply this formula because the design parameter appear on the right side now. Okay, of course, when we apply this formula, we need to know, right, what is the phi and gamma, because now the problem becomes this one, right? So therefore, when we apply this formula in the original one, those phi actually corresponding to the phi gamma, right? This gamma corresponding to C transpose, this L, right? Again, now design parameter correspond to K transpose. Therefore, we just use this one and then apply this formula. So what is the controllability matrix, right? The controllability matrix is gamma, phi gamma, but here this phi is phi transpose, right? Then this gamma is C transpose. That's why I have the C transpose, the phi transpose C times C transpose. Okay, and then we realize actually this one, after some manipulation, you can prove this one equals to this matrix, the transpose of the observability matrix. Then hop. So eventually, what you can get, so this K, then therefore, what is K transpose? You apply this formula, right? You will already have this WC, right, becomes WO transpose. Now, of course, this AM. Now we use the A naught, another desired polynomial, right? The phi is phi transpose. After some manipulation, actually you will get this formula. This is the formula for the observer design. Essentially, because I want to get K, not K transpose, right? So therefore, I just do the transpose again. Okay, of course, this is the Eichmann's formula, and you can use the other way to do it, right? You don't use the Eichmann's formula. Don't like this, right? You can just do the directive comparison, right? You get the correct polynomial. You get the correct polynomial of phi minus kc directly, and then you look at the coefficients. You have a set of equations. When you apply this Eichmann's formula, right, this W involves the inverse of this observability matrix. So therefore, the system has to be observable. Now, is it possible to make the estimation perfect in finite steps? In other words, cannot make the arrow go to 0 in finite steps. All right, so this is the equations for the dynamics of the arrows. Now, we start from the beginning, right? At the first step, it's 5 minus kc times e. The second step, right? 5 minus kc e to the k plus 1, it becomes 5 minus kc squared. At the end step, becomes 5 minus kc n to the power of n ek. Can we make this one 5 minus kc to the nth power equals 0? How do you choose k such that you can make this happen? Or what are the poles of this matrix 5 minus kc? All the poles should be 0, right? If you choose this one as this polynomial, a very simple one, all the poles to be 0, and we know the matrix satisfies its own characteristic equation, right? Then those 5 minus kc to the power 1 equals 0. Is that clear? So you can say we have used this Eichmann's form. We have used the Cayley-Hamilton theorem many times. It's very powerful. Then the observation error goes to 0 at most n steps. This is what we call the deadbeat observer. It looks very beautiful, but in reality, right, we don't use it. There is no free lunch. The deadbeat observer is very sensitive to noise. Okay, so although in theory we have this one, but we don't use it. Now let's summarize what we have learned about the output feedback controller. Remember, we are going to solve the problem where not only the output information is available. We cannot measure all the state variables. Okay. The first step, the controller design. Even though the state variables are not available, you still assume at the first step, you assume it is available. You design a state feedback. Okay. And you choose L such that the closed loop matrix 5 minus gamma L has a desired characteristic polynomial. This characteristic polynomial is from the desired one is from the reference model. Can be calculated by Eichmann's formula. Or you can use the direct comparison. Right? The other way is that you do it in this way, right? You get the correct polynomial of closed loop and match the coefficients. Then, because X is not available, we have to estimate it. So you have to design an observer to estimate the state variable. You have the design observer. This observer will depend upon the information from the input and output, and then they will try to compute the estimated state. So this is the form of an observer. It uses the model of the plant, but it adds a correction term, right? The feedback term. Okay, and then it turns out that aerodynamics, right, will depend upon the gain k. Therefore, you can choose your k such that this observer matrix 5 minus kc has a desired characteristic polynomial a naught z. Remember, this a naught z is different from the reference model, right? You can design that. Then the k can be calculated by the Eichmann's formula, or you can use the direct comparison. So finally, the last step, don't forget, this will be the final form of your controller. You are going to replace your state vector with its estimate. That is the whole picture of the output feedback controller. 3 steps. I repeat again. The first step, you solve the simplest problem, right? Right. All the state variables available, get the answer. You design your error. Because the state variables are not available, then you design the observer. This is the observer, okay? And then you get the answer, right? Design your K. You say, you can estimate the state variable, but in your observer, you estimate the state variable by X height, right? Because X itself is not available. So don't forget, the final answer should be minus L times the estimate of the state variable. Is that clear? Any questions? Okay, now here I want to mention one common mistake made by the student. Let's say in your final exam, ask them to design a state feedback. Okay, then they give me the answer. They have the phi gamma, they use Ackermann's formula. So they just tell me, they give me the K, they give me the error, and then they give me the K. They don't write anything about what is the controller, what is error. They don't even mention what is your state feedback. And finally, they don't mention what is minus L times X. What is the observer? When they design the observer, they just give me, they say, just give me the answer K. What is the observer? This is the observer. So you have to write down the details such that I know what are the numbers you are calculating. Finally, you just give me the answer L and K. Probably you are going to lose 50% of the marks. Okay? You just tell me you know how to apply the formula. I don't know whether you understand the meaning of this formula. Okay? So that is a common mistake, right? I want you to, don't repeat those silly mistake, silly mistake. All right, finally, we have to consider the effect of the disturbance. So far, right, we didn't consider that. So in this model, we say, okay, there's nowhere for the role of the disturbance appear right here in this model. We only consider, okay, the state depends upon the current state, depends upon the input. But we know in reality the disturbance may occur at any moment and everywhere, right? There are many types of disturbance. The load disturbance is the most often encountered. That if I have antenna, right, there may be sometimes there's the wind, right, blows on the antenna, or on the ship, right, there may be waves, right, hitting the ship. Or for a motor, there may be a load. Suddenly there is additional load on the motor, or for the temperature, there may be variations in the temperature. So those are the many types of the disturbance you may encounter in the world. And also there are other disturbance like the measurement noise, right, the errors. Even though, of course, in reality, all those disturbance looks very complicated in different forms. But like I mentioned, right, when we build the mathematical model, the model itself may be simple because you never, there are only good model and bad model. There are no true models. You don't expect, I want to get a perfect model which can describe the true reality. You cannot do it, right? So we always use the simple models to describe that. The simple models for the disturbance could be a pulse disturbance, could be a step, right? Or could be a ramp disturbance, or could be a sinusoid. Okay, in the following, I'm going to give examples of the disturbance, and then you to tell me what kind of model, right, you can use to model this type of disturbance. Okay, this one.
العسكرية العملاقة كان هذا مجرد اختبار لأطلاق التوربيدات، والهدف هو هالسفينة الحربية اللي بزيد عمرها عن 30 سنة، لكن هالدمار يلي صار هو شيء حقيقي. خلونا نشوف مرة ثانية كيف ينفجر بطن السفينة الفولاذي بقلب المي. بتحول الموجة الصادمة وسط السفينة الحربية لكون عين من الأنقاض.
If this happens, you call that disturbance. Which model you can say is the best one to describe? That will be the pulse, right? Heat, it's heat in a short period. And then also for the ship, shall we use a step or sinusoid? Right, you can say it's kind of a periodic motion, right? It's not just a constant. So it's better to use sinusoid. You see, even though the reality is very complicated, but in terms of the model, right, I can always use a simple mathematical model to describe it. Okay, now let's consider the disturbance rejection problem. We want to minimize the effect of the disturbance. So how are we going to do it? So then we have to look at the model again. So we have to build a model to describe the effect of the disturbance. So in addition to the input, there is also a disturbance affecting the system. Therefore, in addition, right, this is the original model, phi gamma. I have to modify it such that it can take into account of the effect of the disturbance. So we have to add those phi x omega, that's a matrix times this disturbance vector omega k. The disturbance itself may satisfy its own equation, right? If it's a constant, then this one is identity matrix, right? But it may be a periodic motion, and then this phi, you'll get the eigenvalues, right? Those eigenvalues to be marginally stable. This yk is the same as the original one. So the output still depends upon the state vector. So but now, so we compare this one to this one, we add the effect of the disturbance. Well, the first question, we know that disturbance, right, happens. Can we just simply turn a blind eye to the disturbance, right, as if it does not happen? So we simply ignore the disturbance. If we ignore the disturbance, what would happen? First, in reality, we say, okay, something must have, will appear, right, differently with or without the disturbance. Mathematically, let's check it out, right? If I just only still use the same controller, right, as if there were no disturbance, then let's just plug it in, right? This uk is just minus air x, so therefore I have phi xk plus this phi omega k plus gamma uk. Then this u is air k, right? You plug in, then we have this phi minus gamma times Lx plus there is additional term omega k there. If you look at this equation, in the simplest case, let's say I make the system stable, right? Phi minus gamma L is a stable matrix. I choose my L in such a way. Then for the stabilization, I want x go to 0. But if omega k is a constant, will the x go to 0? You have a stable disturbance, you have a stable system, but is affected by a constant. The output will be a constant, right? This is from mathematics, and now I want you to see here we can show example that with or without a disturbance rejection. If you add a low disturbance, you can say there is a difference. This one is that if you don't consider the disturbance, right, you can say it will just fly away. This one we say, okay, in the controller, I include the disturbance term, right? We have to do the disturbance rejection. If I add something, it still stays there, right? Okay, so we have to deal with the disturbance. So the disturbance cannot be simply ignored. We have to find out a way to address them, to improve the performance of the system. Okay? All right. Let's look at this equation again. And then let's ask the question, what is the state of the system? Let's recall the definition of the state, right? At the first class, we say state, that is the information we can, such that we can predict the future, combined with the information about the input. If there is a disturbance, can we, if we know this X and the input, can we predict the future, xk plus 1? Look at the equation. Yes or no? We cannot. Right? We cannot. So therefore, for this system, because of the disturbance, right, what do we need to predict the future? In addition to x and u, we need omega, right? Is that clear? So we need x, omega, and u. Okay, now from the definition of the state, if we consider this input, well, we only include u as the input, we don't consider the omega as the input, then what should be the state? Should be both x and omega, right? Therefore, should we include the disturbance omega as a part of the complete state if we don't consider it as input? The answer is yes or no. I already give you the answer, right? It has to be a part of the state. Therefore, we have to define a new state vector. We call the augmented state vector. This is zk, which include both x and omega k. Is that clear? Such that that will be a complete state vector. Otherwise, with only x and u, we cannot predict the future. Therefore, we define a new one, right, which will be a vector with a higher dimension because it includes not only x but omega. Now let's write down the equation for this new state vector. Of course, it's the same equation but with a new notation, right? Z k plus 1. I put those two equations together. This will be a matrix, right? Include both phi x omega, phi omega, this times z, gamma, 0, right? Here, y equals just C0 times z. I just rewrite this equation by the new notation, z. Then if I look at this form, right, is it in the standard form of a state space model now? This is the state, right? Depends upon the current state and the input. Yes. And that's what we need. Okay. Now, how are we going to solve the problem? So, first step, as in the output feedback control, right, we assume the state variables available. Here, we also assume that the state vector z is available. Then we design a state feedback controller. But they include both x and omega. So therefore, we design controller assuming x and omega are available. So we design this RC. So RC include two parts. One is again on the x. The other one is L omega on the disturbance. Now you may argue, right? Hey, you see, in this step, we assume that the disturbance is accessible. Is this assumption realistic? Disturbance is not accessible, right? No. But remember, when you try to solve a complicated problem, you always start from the simplest case, even if it is unreal. We know why do we call disturbance? Because it's unmeasurable and also is the timing of the disturbance is also unpredictable, right? But we first solve the problem. Actually, we know when and the disturbance happens, and also right the type of disturbance. We have the complete information about this disturbance. But actually, this is the most important trick in doing good research work. You first have to get an answer for the simplest case, even if the case will never happen, right? In reality, never happens. But you have to get the solution to that ideal case. All right. So even though we know that the disturbance we cannot measure, we still assume that it's available. Let's say if under this condition, what we can do. Then we look at the closed loop. Let's look at the closed loop, right? Let's plug it in. This U, right, will becomes this one. And then we organize. This will be the closed loop equation after this controller. There will be two new matrix, right? This phi becomes phi minus gamma times L. This phi x omega becomes phi x omega minus gamma times L omega. So we have two gains to design. How do we choose L? So we choose L to change this matrix. Okay, this one we have already solved. We choose L such that phi minus gamma L has desired poles from this reference model. Then there is some new design problem we have to solve. How we're going to choose the L omega, right? Well, we say this is the disturbance rejection problem, right? Which means I want to choose L omega to minimize the effect of the disturbance. In an ideal case, right, I may choose L omega such that this full matrix, right, phi x omega minus gamma L equals 0. That's a very special case. It can happen sometimes. Then in this case, disturbance can be completely cancelled out. But what if it is impossible to make this one go to 0? If this happens, right, we need to analyze the transfer function from the disturbance omega to the output. Now, because we want to analyze the transfer function, we need the Z transform, right? We do the Z transform on this closed loop. Okay. So this one, xk plus 1 becomes zxz, right? This one, okay, phi minus gamma L xz plus this one. Then we get the solution of x, right? In terms of omega, then we get the transfer function. So y equals c times x. But x, right, replaced by this expression, then we get a very complicated form. But anyway, in this way, we can get the transfer function from the omega to y. We use h omega to express this whole thing here. Therefore, we know that the disturbance will affect the output, and we know the transfer function. Okay, now here comes the problem, right? We want to minimize the disturbance. Okay, Then it will depend upon, you have to know what type of disturbance you are dealing with, such that we can minimize the effect, right, of this disturbance on this output. In a simple case, we say, okay, the disturbance is a constant. We don't know the value of this constant, but we know, okay, it is a constant. Now here comes the problem. For a system, if the input is a constant, I want to minimize its effect, which means I want to make the output to be zero. Is it possible to design a system such that the input is a step, the output is zero? Or in other words, the steady state gain or the DC gain is zero. We know the DC gain, that's the value of the transfer function when z equals 1, right? But remember, this h omega, this transfer function depends upon your design parameter L omega, right? So you know that the gain will, the steady state gain will depend upon your design parameter L omega. So therefore it can, you can't just design, you design the L omega such that the DC gain of this transfer function to be zero. Is that clear? If you achieve this, which means you don't know the value of the disturbance, but you know it is a constant, and also you know that eventually the effect will be zero. Is that clear? Any questions? Then in the same fashion, you can think about, you can also deal with the sinusoid, right? Remember, for the frequency response, if you know the frequency of the disturbance, you can design, right, the frequency response, the gain to be zero by choosing, right, by choosing the L omega. Okay, but now here I just give you a simple case. So anyway, so you get the transfer function. As long as you have to have some information about the disturbance, what type of disturbance, right, the frequency of the disturbance, then you can minimize the effects of the disturbance. Okay, so here we solve the design problem for the first step, right? We assume that we know the disturbance, we know the state variables. Of course, in reality, we don't know. Both x, right, the state variable and the disturbance are unknown. What should we do? But have we already solved the case when x is not accessible? We build observer, right? So therefore, you say, okay, the step 2, you just design the observer to estimate both x and disturbance. Not because as disturbance can be treated as part of the state. You look at this equation, right? X is a state vector. Z is a state vector, right? Z includes both x and omega. But of course, the dimension of this new state vector is bigger than the original one because it includes an extra term. But anyway, it is in a standard form, right, for state space model. So as long as this model is observable, you can design a observer. But remember, this observer, this matrix, right, has been enlarged, right, from phi to this a bigger one, and then you can design your case. You choose your case such that the correct polynomial of this matrix, right, match any desired one. At least they have to be stable. In this way, you can estimate both x and the disturbance omega. Okay, so even though they are not accessible, you can build an observer to estimate them. So once you estimate that, don't forget the last step. This will be the final step. So your final controller depends upon the estimate of the state, depends upon the estimate of the disturbance. Okay, any questions? Let's try to solve one problem. The double integrator again. So here, the double integrator is affected by a load disturbance omega. Now, this is a load disturbance, so there is a constant disturbance. For constant disturbance, just say, okay, omega k plus 1 equals omega, right? It's a constant, but you don't know the value. Step one, right? We have to choose my air and air omega such that we can eliminate the effect of the disturbance. How to choose air? Choose air is just a pole placement problem, right? We place the poles to the desired ones from the reference model. For this simple problem, how do we choose air omega? You look at the form of this equation, and then you can choose air omega in a way such that the effect of the omega can be completely eliminated, or you can make this omega disappear. How you choose air omega such that in the closed loop equation, the omega can disappear? What can you say that? What is air omega? Air omega cannot be zero, right? Air omega is zero. It is still there. What is air omega? Can you say that? Plug in the UK into this expression. What is air omega? I want to reject the disturbance, right? Somehow, what is air omega? Easy, right? You just put air omega as 1. You plug it in, disappear. In the closed loop, there is no air omega. There is no omega, right? So this is the ideal case, which actually you can completely eliminate. You just design your air omega in this way. You plug it in, there will be no there will be no omega. The problem is solved. But of course, this is the case, right, where you know the omega. So we have to build the observer. So build the observer, you have to use the augmented state. You have to rewrite this equation. So the new state include both x and omega, right? Therefore, this is copy this one and this one. We put it here, omega k plus 1 equals omega k. And for this control vector, right, the input does not affect the omega, and then this is the output. Okay, then you have this equation that you can build the observer. The difference between the observer for the disturbance rejection case is that the dimension has increased because you want to estimate both the state vector and the disturbance term. Okay, is that clear? So now for this third order system, right, you design your K. Then the K, of course, will be a 3-dimensional vector. You choose K to place the pose for the observer aerodynamics. Of course, for many of the problems, just to simplify, right, the design, you can just choose, okay, this one, the aerodynamics, you can say, okay, I want to make the arrows go to 0 as fast as possible. You can choose the simple one, the dead bit, all the poles to be zero, at zero. Finally, right, this is the last step. The input is just the minus L x height, right? We replace the state and disturbance by the estimate. This problem is simple because of the first step, the way you choose L omega, because of this special form, immediately you can tell the L omega equals 1, right? But in some other case, it's not so simple. Then you have to get the transfer function from omega to the output and try to find out, right? Because this is a constant disturbance. You want to make the DC gain of that transfer function to be 0. But I choose this problem just to save time, right? But there are more complicated case you can work out. Now, let's look at the limitation of the controller we have discussed so far. This is the open loop, right? This is the open loop. And then we do a purely state feedback. This is controller we have designed. Okay. Then the closed loop becomes this, just phi minus gamma L xk. Well, if this is the controller we're going to implement, what will be the steady state output when this closed loop is stable? What will be the output? Is it a constant? Yes, it is a constant, but that constant is 0, right? Because x will go to 0. So of course, y will also go to 0. But in reality, right, normally I don't want output to go to 0. I want output to probably go to some constant. So, but in this case, we say, okay, if we only use the feedback control, then the output will go to 0. Therefore, because the purpose of the feedback is to change the internal property of a system like the poles, if the objective is to make the output follow the common signal rather than 0, then we need to add a feed-forward control signal to the system. In other words, what we need to find out, so here is a feedback term. We need to find out the proper value for the feed-forward signal, control signal. Okay, this will be the final part of today's lecture. For the power placement, right, it's just stabilization. But for the tracking, at the beginning we said, I want to follow the reference model, not only just place the poles, I also want to place the zeros, right? Not just AN, I'm going to take care of the zeros. Then this is what we call the tracking problem. Now, how are we going to match the zeros? In the output feedback control, right? This is the controller we use. The controller is purely feedback without any information from the common signal. Now it's time to add the influence of the common signal because I want output to follow the common signal such that we can make the transfer function. So finally, I want to make the transfer function from the common signal to the output to match the reference model, not just match the poles. Okay, so therefore it involves both the feedback and the feed forward. Let's look at a very simple approach we call a naive approach or the just proportional control. The feed feed-forward control signal, I just make it proportional to the common signal. So LC is a constant. I design that. Okay, and say, would that work? Let's try to work it out. Here, right, and then this is the feed-forward term, right? I want to add this to this original feedback control. So there finally I have minus x hat plus LC times UC. Let's try to analyze the closed loop system. So I have xk plus 1 equals phi xk plus gamma u. This is the original model. This is the output. We use the output feedback, which means I need to design an observer to estimate the state. Then this is the input, right? Input, not only consider the feedback term, I have the feed-forward term, which is a simple way, just LC times UC. Okay, let's try to get the analyze the signals. We say, let's define the estimation error from the observer, right? And then we'll simplify the equation right here. After the feedback, we plug it in. This is what happens. The x k plus 1 equals phi minus gamma L xk plus gamma L ek, the estimation error, plus there's some extra term, right? Gamma LC UC. And the estimation error, okay, I base this equation phi minus kc ek, but we know I will make it stable, right? So we know that the ek will go to 0. So therefore, we will set the ek to be 0. Then those yk will be c times xk. Now let's remember what we are interested is the transfer function from the UC to the output. I want to make that transfer function to follow the reference model, right? Okay, so now let's get the transfer function from the UC to Y. Okay, and then we can say to get the transfer function, we just use the Z transform, right? Use the Z transform, I can get this one. Zx equals phi minus gamma Lxz. Remember, because E, right? When we get the transfer function, we don't consider E here because E will go to 0. So gamma LCUC. Then we can express X by UC. And then we can get output Y, right? Is C times X. But X is expressed by UC. In this way, we get the transfer function from the UC to the output. It can be shown, okay? It can be shown that this transfer function, right? Because we design an error such that it will match the poles. So the denominator is just AN from the reference model. Okay, here it can also be shown, because of the time, I'm not going to show it here, that actually this transfer function, the B is from the original transfer function. So the pure state feedback control does not change the zeros. It only changes the poles. The original transfer function is B over A. Okay, so here we keep the same B. And then this LC is a constant, right? Is a scalar again, because this is the way we call the simple approach. And this will be the transfer function from the common signal to the output. Okay, here this step I don't have time to prove it, right? But if you're interested, you can show it by yourself. But anyway, so if we follow this approach, this will be the transfer function from the common signal to the output. What's the objective? The objective, I want to make this transfer function to match the reference model, right? PM over AM. Now let's try to choose LC such that, right, this one match this one. Then I get the answer, this LC should be PM over B. But at the beginning, right, we say this, I want to take a very simple approach such that LC is just a proportional gain. It's supposed to be a constant. But it turns out, if LC is a constant, then those two cannot match unless LC is chosen in this form. So then what does that tell you? It tells you that you have to, right? The original design cannot work. You have to modify your design. Actually, here it already shows you the answer for your design. Instead of a constant, you should replace LC by a transfer function, right? We have to increase the freedom of the controller. Those LC is the original design, right? We say LC is a gain. But we know it doesn't work. It turns out LC has to be in this form. Well, we can also, do some logic analysis. Where can we find the extra freedom? Can we change the feedback controller? Shall we change L? If we change L, we already design my L to place the pose, right? If I change L, I'm going to change my pose. The only extra freedom is this block. We no longer require L to be a constant. So I just require it to be a transfer function. What does that mean, right? What's the difference between a constant and a transfer function? It means if it's a transfer function, a constant, it's not a dynamic system, right? The output equals the input times a constant. If it is a transfer function, means it's a dynamic system, right? The output depends upon not only the current one, right? Depends upon its history. It will be described by a difference equation. The output will be a linear combination of the past values of the input and output. When we say okay, system is a transfer function, so it's no longer a static system, it's a dynamic system, right? It depends upon the history. All right, so finally, actually, we have this, what we call the 2 degree of freedom controller. So this is probably a new stuff, right? You have not learned when you were undergraduate. In the undergraduate, normally, right, you have a plant, you have a controller. You only design one controller. This is the system you want to control. This is the standard we call a unit feedback control system, right? You just design one block for the controller. Here, you want to match both the poles and zeros. Then it means you'd better have 2 blocks, right? One is for the feedback controller design, the other one is feed-forward controller design. So we have 2 degree of freedom controller. For the feedback is for the power placement. The feed-forward is for the zero placement. And the feed-forward, I give you the answer is just PM over B. Then we can compute the transfer function. If we follow this approach, right? This approach, this transfer function is just we have shown that it should be LC times B over AN. But LC is BM. Here I replace LC by BM over B. But you may say, hey, I did the first two lectures. Always you have to be cautious when you should cancel out the common factor, right? Here I say I should cancel out. In this case, why we cancel out this B? We say under what conditions should we cancel out if the B are operating on the same signal, right? Actually, if you look at this B here, right, is operating on the feed-forward signal. This B is also operating on the feed-forward signal. Okay, that's why they should be cancelled out. Then, therefore, indeed, it will match the reference model completely. Any questions? We can follow the reference model completely because here we trying to use the model reference control, right? We will, because the reference model will follow your trajectory, your desired trajectory. The reference model will meet all the requirements. Here we follow the reference model. Then whatever the reference model can do, your closed loop system can also do it. There's no need. You design, you can, okay, there's easy way, right? The easy way when you design your reference model, you can design the gain of your reference model, let's say to be the d-secant to be 1. Therefore, when the UC is a constant, your output from your reference model will be the same constant. You just design your reference model in such a way it will meet all your requirements. Okay, any other questions? For example, right, for air conditioning, right, you design reference model such that your gain is 1, right? Okay, so therefore, when you set if your common signal is 25 degree, your output will be 25 degree because the gain is 1, your reference model. And then you build your controller to match your reference model. And also the reference model, you said, I set my settling time to be 1 minute. If you follow the reference model, your control system also can achieve that. The settling time will be 1 minute. Okay. Of course, you have to design your reference model carefully such that it can meet all the requirements. This is the way, right, to solve the one way to solve the control problem. There are some other ways. In this course, for my part, I just focus on this way. Of course, in the lecture 6, I will talk about some other ways that was okay. I don't use the reference model. I just try to follow, right? You give me the desired output, I try to follow it. Yes, it can be done. It can be done. By a different way, you are going to learn that. That's what called the model predictive control. Okay, that will be the second part of this. This is the simple way. So we can any other questions? So we can match the reference model completely, right? Now, this is what we call the 2-degree freedom controller. There are 2 blocks to design. This is the original, right? Open loop transfer function is B over A. After using the 2-degree freedom controller, we can match the reference model. Now let's recall what we have learned, right? We have covered so far, and what are the conditions? Can we solve the tracking problem completely for any linear system? What are the conditions? Do we require the system to be controllable? We do, right? Otherwise, if not controllable, then some of the poles may not be changed. Do we require the system to be observable? We do require, right? Otherwise, right, we cannot estimate the state variables. Now, do we require the open loop to be stable? Of course not, because we can change the poles, right, to anywhere we like. That's the whole point of feedback. We can make the unstable system to be stable, right? So the open loop, the poles of the open loop come anywhere. Now it looks like everything is in place. But finally, let's check out whether all the signals are bounded, right? We do not want to have a situation that some of the signals may blow up. Let's first look at the output. Is the output bounded? We know this is the transfer function from the common signal to the output. It follows the reference model. Of course, unless you design your reference model to be an unstable one, right? Of course, sometimes you want to do it, right? You want to sabotage the system. Now, is the input bounded? Then we also have to know the transfer function from the common signal to the input. Then we know whether it is bounded or not. Okay. So this one is easy. We know the transfer function from common signal to Y, right? We also know the transfer function, right, from the input to Y. From those two, we can take the transfer function from the common signal to the input. And we have this form. It is not only Pm over An. Actually, we also have A, right, over B. But look at this expression. So we have a transfer function, right? This is the input. You can consider, okay, the common signal is input. This one, the input signal is output from this system, and this system has to be stable, such that this U input, right, U is stable, right? Then what's the condition to make this stable? We know, of course, Pm over Am is stable. Then how about B? Can you say that? The B has to be stable. So here we have a very strict requirement, right? The system is required to have a stable inverse for perfect tracking. At one of the classes, we said that this is one. So why we were interested in the inverse of a system, but here this is the condition we have. If you want to have a perfect tracking, okay, then the requirement is very strict. If you don't require that, right, you don't want the perfect tracking, right, you don't need this condition, right? I can place the post. Whether I can place the zeros to anywhere you like, we need this condition. Is that clear? Otherwise, your input may blow up. That's not what we want. Huh? Now, after explaining this condition, now can you tell me the answer to this question? If I just want to stabilize the system, do we require this condition? We don't require this condition, right? We say for pole placement, I have no condition, right? As long, what's the condition to solve the pole placement problem here? System is controllable, right? We require this condition only if we want to have a perfect tracking. Okay? Right. So let's summarize, right? What we have learn to solve the state space approach problem, right? We try to match the reference model. So we first design the state feedback controller air. And then your first step, you assume that you know everything, right? You know all the state variables. You design. If there is a disturbance, you also assume that you know this disturbance. You design the air omega. And then the next step, right? You assume that you don't know them. Then you build observer. Estimate the state variables and the disturbance. And the final step, right? You design your feed-forward controller. So there is a 2 degree of freedom controller, right? There are 2 blocks for you to design. How to choose air is the pole placement, right? You match, right, the poles of the closed loop to that from the reference model. How to choose air omega? This one will be problem dependent. Our air omega will depend upon what type of disturbance. It depends upon the structure of the model. How to design the observer? That's another pole placement for the observer, right? You design your case such that, right, the poles will match the poles from another polynomial A naught. How to choose the feed-forward transfer function? This one is simple. I will already give you the answer. It's just Bm over B, because I want to cancel out this B. That is the zero placement. Now, finally, at the B, right, this B has to be stable for perfect tracking. If we want to follow this reference model completely, we require a stable inverse condition. Okay? Any questions? All right, so that will be all, right, for the lecture 4. Then the next week, well, we have 2 more classes to go for part 1. I'm going to release the second homework assignment. That's all. Thank you. Yeah.
A good question. When we choose the L omega,
Yes.
we also need to